Welcome to my virtual OpML 2020 talk on our experimentation and analytics framework for large-scale AI ops platforms. I'm Thomas Rausch. This is joint work with Waldemar and Vinod Muthusamy and was the result of a research visit at IBM Research AI I did in 2018. So I first want to motivate this work by explaining why we needed this experimentation and analytics framework and what type of AI ops platforms we're talking about. This idea of operationalizing AI has really become pervasive throughout industry and academia. Putting your ML models into production involves several things. So first we need the workflow steps necessary to create the model. And then we also have the runtime aspects of new data arriving, model performance monitoring, and the subsequent triggering of retraining loops based on some rules. And I'll talk about these things in more detail later. There are different names for this idea. We call it AI ops, and its importance is made evident by the many industry platforms that already exist, and also the academic literature in this area, to which we have also contributed in the past. What emerged for us were three views on AI ops. First, you have the user's view, whether they are using a UI or a declarative configuration model. Users want to plug together a workflow to process their data, maybe debias it, configure a training procedure, maybe run some custom steps like compression, and then validate and deploy their model. So we can model this pipeline basically as a workflow, so a DAG of domain-specific tasks and conditions. And then we have the platform view, where the platform is responsible for orchestrating and executing the workflow on our infrastructure. Typically, the platform sits on top of some storage system, compute infrastructure, and a learning infrastructure with specialized IT resources. So in our case, when we run a training task, it will retraining data from Cloud Object Store, execute your ML code on the GPU cluster, and then store the serialized model back to the object store. Once we've deployed our model, we want to make sure that we automate the retraining procedure, creating these automated continuous training loops. So maybe you want to trigger the pipeline periodically, or when performance drops, a certain number of new data are available, or in other words, if your model gets stale. So it's clear that platforms will have many of these pipelines waiting to be scheduled, and there's a cost-benefit trade-off between retraining and the model performance gain achieved by running the pipeline. So say a pipeline is scheduled to run every few weeks, but there are no new labeled data available, running the pipeline may not have a significant effect. So what we were now thinking about was to create a pipeline scheduling strategy that would optimize schedules towards probabilistic parameters such as the expected improvement of running a pipeline on a model, or the risk associated with running the pipeline, and also consider the available resources or budget. We started to formalize this as a scheduling problem, but quickly ran into some roadblocks. For example, at the time, there was no system model for AI ops platforms that we could build on, and it was also not clear how we would test and validate like a scheduler. So to move forward, we really first needed a framework in which we could develop these types of operational mechanisms. By modeling the pipeline execution, generating synthetic data and pipelines for a simulator, and use this to study the system behavior. And this really requires a good fidelity, trace-driven simulation. So our ultimate goal was to develop operational mechanisms that orchestrate pipeline executions on our platform's components. We had analytics data and traces from a real system, which we used to model and parameterize the simulated system, feed that into a discrete event simulator, and then use the synthetic traces to do exploratory analytics and also create the predictive models used by the operational mechanisms like a scheduler that we were proposing. The rest of the talk will focus mainly on these two parts. So I'll first talk about the system model and then give a quick demo of the simulator and tools we have so far. While developing the system model, we examined traces of several hundred thousands of pipeline executions to extract the most relevant parameters. Overall, the key aspects are the system model, a way of generating synthetic pipelines and data as input for the simulation, and a process model that describes how things are executed. As we talked about earlier, an AI ops platform really has two orthogonal views. One is the build time view that describes how models are generated from input data, and the other is the runtime view that describes how the system behaves once models are deployed and how model metrics change over time. The core concepts are really these pipelines and the individual tasks. How the tasks are executed is described by a task executor. For example, a training task involves reading from a data store, running the code on the training cluster, and then writing the serialized model back to the data store. So these are all events in our discrete event simulation that simulate the task execution, which then generate the synthetic traces that can later be analyzed. And you have your compute infrastructure and your data stores as resources. In our case, we only modeled compute and learning clusters as discrete resources. So each task gets a certain number of workers from the cluster, but you can extend this depending on your particular system. The runtime model is not yet fully implemented, but in principle, what we want to model is the change of model or data metrics like confidence values, concept drift, or some aggregate metrics like staleness factor over time. So we evaluate these at discrete events, namely when scoring happens or new data arrives. Rules then trigger the retraining process, which would then again use the build time model to execute the pipeline. I'll talk about some of the open problems in the runtime view later. To set up an experiment and a simulation run, we want to randomly create pipelines that are plausible and the data used as input for these pipelines. So the question was what types of parameters the pipelines and the data had that we could describe and then sample from our trace data. Creating plausible pipelines randomly was difficult because at the time we really didn't have a lot of data on custom pipelines. So we had some knowledge. So for example, the simple process train evaluate pipelines were already fairly well understood. We knew that people were adding model hardening and compression steps to their pipelines and things like bias detectors. And we also found that hierarchical pipelines were becoming more relevant, that generated, for example, user-specific models from a base model using transfer learning. There really aren't a lot of generalizable properties of pipelines that were immediately obvious, but we looked into platform-specific properties. So, for example, the particular ML framework used by the pipeline, and I'll talk about this a bit later. To create a synthetic data asset at runtime, we really just wanted to sample from the parameter space. So we abstracted data assets down to three properties, basically columns, rows, and the size of the data asset in bytes. The graph shows data from Data Refinery, which was the data processing platform of Watson Machine Learning. And here you can see a density plot of data assets that were in the system. It's a reduced view where we collapsed columns and rows into one axis and plotted it against the size in bytes. Basically, all we did was transform the data into an appropriate space to fit Gaussian mixtures, from which we could then sample at simulation time to receive a synthetic data asset. So now at simulation time, whenever we simulate the creation of a pipeline, we first sample from this Gaussian mixture to get the dimensions and the size of a data asset that is used as input for the pipeline. For the process model, there were three main questions to answer, namely how long specific pipeline tasks execute, how frequently pipelines are executed, and how the model metrics change over time. For modeling the task execution time of data preprocessing steps, it was easy to now correlate the size of the data asset with the compute time of the preprocessing step, which is the relationship that this graph shows. So we just fitted an exponential distribution on this, and at simulation time we sample from this function where we just pass the properties of the generated data asset and add some log normal distributed noise. Modeling the ML training step accurately is a bit more difficult, but we found that in our system, the ML framework was a good predictor for the execution duration. This is not to say that PyTorch performs worse than TensorFlow, but our users tended to build more complex models using PyTorch. So when we synthesize a pipeline, we assign the task an ML framework, and we can then sample from the stratified distribution and get a pretty good simulation of the task execution duration. Each pipeline task has to be modeled like this in some way by correlating the execution time of the task to some parameters we know about. For generating workload, we took a standard approach of modeling pipeline interarrivals, which fairly unsurprisingly were exponentially distributed. We found that Weibull distributions were the best fit, but classic Pareto distributions also work. And typically these functions have a long tail. Obviously, there are human factors involved in these platforms. So when modeling workload, it's important to consider variability during time of the day. For example, here you can see the average arrivals per hour on a typical Monday, where people often submit their jobs just before their lunch break, which is the second peak that you're seeing. And you can see the significantly lower workload on weekends. So it was important for us to capture this, and what we did was to stratify the interarrivals into 168 clusters, one for each hour and weekday, fit the Weibull distributions on each of the clusters, and during simulation we would map the simulation time to a real time and draw from the specific cluster given the current time and day. As I mentioned before, the runtime system model is still a work in progress. For example, we haven't yet explored what the arrival process of new data labels are, or how often models are scored, and subsequently how the model performance metrics change over time. So there are a lot of open questions regarding the runtime behavior of the system, and we hope that the community can help us with their experience reports and data on these questions. Other open problems include the conditional modeling between pipeline tasks. So for example, the duration of a validation task likely depends on the result of the training task and the data preprocessing task. Also, these platforms have some user churn associated with them. So on the right-hand side, you can see the growth of unique users using the platform over time. And on the left, you can see how the use of specific ML frameworks change over time. This is relevant, obviously, if you simulate the system for a longer period of time. I want to give you a quick demo of the simulator and what we have so far. So our simulator is built with SymPy and integrates nicely with Python's ecosystem of data science tools. Here you can see the definition of an experiment. This is the duration, so the number of seconds we want to simulate, the profile used for generating workload, a factor to control the scale of the pipeline interarrival distribution, a mapping to a real time, and a parameter for the capacities of our infrastructure. So running this takes a few seconds. It's simulating 1 day of pipeline executions, and in total took roughly 5 seconds to simulate almost 2,000 pipeline executions. If we go to the dashboard, we can see the experiment parameters. For example, the arrival profile, the size of the compute and learning cluster, and so on. We can see the number of pipeline executions and the average number of tasks per pipeline, which is interesting because we're randomly generating pipelines and their structure may vary. You can see the infrastructure utilization. In our case, we have two basic resources, namely the compute cluster and a learning cluster, but you could easily extend this to add your own. Here you can see the arrivals of individual tasks. In this case, it's a random pattern because we used the random workload profile. And below here, we can see the queuing delay. So the time tasks have to wait on resources. You can see the aggregated execution time of different task types. For example, you can see that the training tasks run from a few minutes up to several hours. And this is the traffic between the object store and the compute resources generated by tasks that fetch and store data. So let's run another experiment with a different arrival profile and scale the arrival distribution to create more workload. And if we run this, check out the data, we can now see that these three peaks that we modeled by our inter-arrival clustering approach. This is useful to test the effect of different arrival profiles on our infrastructure utilization. You can also configure the capacity of a resource. So let's say we want to run an experiment where we reduce the number of nodes in our learning cluster. So let's run this with the same parameters and observe the effect. You can immediately see that the learning cluster is now saturated at the first arrival peak. And we can also observe the consequence, namely that the arrival of subsequent tasks is significantly delayed, which also may have an impact on your compute infrastructure. The other thing we've modeled, which isn't captured in the dashboard yet, is what pipelines are doing with the model. And I want to show you this in InfluxDB, which is where we store the traces. So here you can see the measurement, which is basically InfluxDB's name for tables. And there's a table that stores the changes to the model parameters when running pipeline steps. So I'll write a query that selects from the model parameter changes for the first experiment that we ran. And you can now see some model performance metrics like the clever score, which is a robustness score, the model performance, the pipeline, and the tasks that were executed. So this particular performance data is still randomized, but you could imagine that these data also come from observations of a real system. If we group this query by pipeline, you can also see some of the tasks structures emerging. And this concludes the demo. We investigated the accuracy and performance of our simulation and did some experiments. We've reported the results in a tech report that we recently published on arXiv. So to conclude, we argue that AIOps platforms can benefit from improved scheduling of automated AI pipelines, which will be a significant portion of cloud infrastructure workload. With a good system model that generalizes, the community can start developing these operational mechanisms, and using a simulation framework, we can test and validate these mechanisms with different system parameters. So if you're interested in details or a collaboration, please engage with us via email or on Twitter.